In this video, I'll talk about inference on matched pairs. The Friday the 13th problem we saw was a one mean problem, but it is also what's called a matched pairs problem. So let's take a look at the problem again. We're given a set of data on traffic at certain locations on Friday the 13th and Friday 1 week before, the 6th. There are three columns of data, one for traffic on Friday the 6th, one for traffic on Friday the 13th, and one for the difference, Friday the 6th minus Friday the 13th. We want to test whether the mean difference of traffic between the 2 days is 0, meaning the 2 days are the same, or non-zero, meaning the 2 days are different. So we look at the column of differences, and we test the hypotheses. H0 is that the mean of the differences is 0, or HA is the mean of the differences is not 0. And because there's one mu, that makes it a one mean problem. Now let's back up a little bit. What if we're given the original data set without the subtraction? So it looks like there are two samples of traffic data here. One sample of traffic data on Friday the 6th, and one sample of traffic data on Friday the 13th. And we're asked to test the same thing, whether the mean difference of traffic between the 2 days is 0 or non-zero, whether there is or isn't a difference in traffic on average. So what do? We will recreate the table that we saw at the beginning of this video. We will add on a column of differences of the 6th minus the 13th. So we take 139,246 minus 138,548. But then our little brother, who's home and has nothing better to do, points at this number and says, why don't you subtract that? And we go, what do you mean? And the little kid says, that's Friday the 6th. Yeah, yes, it is. And he points that at this other number down here again and says, that's Friday the 13th, right? Well, yes, it is. Well, so how come you don't subtract those instead? So we tell our little brother, look, we're taking traffic for Friday the 6th from 1990 at location 1. And so if we're going to compare it with Friday the 13th, we must also compare it with Friday the 13th in July 1990 at the same location, same year, same month, same location. It does not make sense to compare it with Friday the 13th, some other month, some other year, some other location. It has to be these two. Our little brother is satisfied with our explanation. He walks away. Well, that's the idea of matched pairs. These two numbers are matched together, as are all the other pairs of Friday the 6th and Friday the 13th. All the other pairs of Friday 6th and 13th are matched together. Once we start with any given Friday the 6th, such as this one, then we know which Friday the 13th has to go with it. So the formal definition of matched pairs is this. We have traffic data from two populations here, Friday the 6th and Friday the 13th, two populations. If the choice of including a given individual to put in one sample dictates which individual must go in the other sample, then that makes it matched pairs. This individual dictates that individual. Now, informally, if you can sense that one individual in one population is tied together with one individual in another population because they share the same something, then that makes it matched pairs. For example, our Friday the 13th and Friday the 6th share the same year, month, location. Other examples of matched pairs include hourly wage of men and women doing the same work. It has to be the same work or it doesn't make sense. weight before and after dieting. It must be the same person. School performance before and after counseling. It must be the same student. And in general, all the before and after situations that we see in real life should be analyzed using a matched pairs analysis. All right, so how do we do matched pairs? Given data for matched pairs populations, first we define the difference. You may choose population 1 minus population 2, or you may choose population 2 minus population 1, whatever makes sense to you. Our parameter is mu of the difference, mean of the difference. If we do hypothesis testing, our null hypothesis H0 would be mu of the difference is equal to 0. And HA would be whatever the question is asking for. You figure out if it's not equal, greater than, or less than. And if it's a confidence interval problem, you calculate the confidence interval of this one mean, the mean of the difference. The conditions are the same as the one mean conditions, because at the end of the day, it's a problem regarding the one mean of this column. So the conditions are either that the two populations are normal, because that would make the population of the difference also normal, or the sample size is large. And then we use technology on the differences, again on this column, to obtain the test statistic, p-value, or confidence interval. Some technology such as StatCrunch comes with a matched pairs function, so you can work with the two populations directly without having to first compute the column of differences. And then we answer the question asked by drawing a verbal conclusion in context regarding the mean difference. And that's how a matched pairs problem works. Thanks for watching. Bye.